What if I told you that somewhere on the floor of the North Atlantic there is a 3,500-ton steel coffin crushed into a debris field the size of 6 football fields, and the men inside never had time to scream? 129 men went down that morning. Engineers, officers, the best of the best, and in less time than it takes you to read this sentence, they were gone. This is the story of how the ocean, silent, patient, and utterly indifferent, turned one of the most advanced machines on Earth into scrap metal in under a tenth of a second. And to understand how it happened, you first need to understand the silent war that every submarine fights. Every single second, it's underwater. Chapter 1. The Invisible Enemy. To understand why a submarine sinks, and why, when it does, there is often no warning at all, you have to understand pressure. Real pressure. Not the kind you feel in your ears on an airplane, the kind that can fold steel like paper. At the surface, the weight of the atmosphere pressing on your body is about 14.7 pounds per square inch. You don't feel it because your whole life, every cell in your body has adapted to that exact number. But descend just 1,000 feet into the ocean, and that number jumps to over 440 pounds per square inch. Go to 2,000 feet, nearly 900. By the time you reach crush depth for most military submarines, somewhere around 1,300 to 2,400 feet depending on the class, the pressure outside the hull is enough to crumple a car like aluminum foil. Now think about the hull of a submarine like a soda can held underwater by a man standing on top of it. As long as that man stands perfectly still, the can holds. The forces are balanced. The submarine's internal air pressure, roughly equal to what you and I breathe right now, pushes outward. The ocean pushes inward. For decades, naval engineers have built submarines as a careful, brutal negotiation between these two forces. But here's the terrifying part. That balance is not gentle. It is not forgiving. It is a knife edge. And if anything, a single weld, a single valve, a single pipe fails at depth, the ocean doesn't gently seep in. It detonates inward. At depths beyond 1,000 feet, a breach the size of a coin can fill an entire compartment with water in under 2 seconds. And the water doesn't pour in like a flood. It comes in as a supersonic blade of liquid, hot from compression, capable of cutting through a human body before the brain even registers pain. And on the morning of April 10th, 1963, that exact nightmare was about to become reality for the crew of one of the most advanced submarines the United States Navy had ever built. Chapter 2. The Pride of the Fleet Picture. A machine designed not just to survive the deep ocean, but to hunt in it. Faster than any submarine before it. Quieter. Armed with the most advanced sonar the world had ever seen. This wasn't just a submarine. This was the prototype for an entire new class. The tip of the spear in a Cold War arms race, where the side that could dive deeper, hide quieter, and strike first, would win. For 2 years, engineers had pushed this design to the absolute edge of what 1960s metallurgy could achieve. Its hull was forged from HY-80 steel, a high-yield alloy strong enough to withstand crushing pressure at depths previous submarines couldn't dream of reaching. Every system on board, the reactor, the ballast tanks, the hydraulic lines, had been engineered to operate flawlessly under conditions that would instantly destroy a conventional vessel. But here's the uncomfortable truth that almost never makes it into the highlight reel. This submarine had just spent months in the shipyard undergoing extensive repairs and modifications, and during those repairs, shipyard workers had installed over 3,000 individual pipe joints throughout the vessel, joints that connected seawater systems directly to the outside ocean. Now imagine this. Each one of those 3,000 joints was a tiny door to the abyss, and for the submarine to be safe, every single one, all 3,000, had to be perfect. Welded correctly, inspected correctly, tested under pressure. Later investigations would reveal something chilling when shipyard inspectors tested a sample of these silver-brazed pipe joints from sister submarines using ultrasonic testing, a method that can detect microscopic flaws invisible to the naked eye. Over 14% of them failed. 1 in 7. 1 in 7 tiny joints, anywhere on a submarine carrying 129 men, had the potential to fail under the crushing weight of the deep ocean. And on this particular morning, this submarine was heading out for a routine deep dive test, designed specifically to push it close to its absolute depth limit, Following alongside on the surface was a support and rescue ship, maintaining constant underwater telephone contact as the submarine descended deeper and deeper toward crush depth. Chapter 3. The descent into silence. 7:47 a.m. The submarine reports it is approaching test depth. Everything sounds routine. Calm voices. Standard procedure. This is exactly the kind of dive this crew has trained for dozens of times. But then, the underwater telephone crackles with something different. A transmission, garbled, partial, mentioning something about minor difficulties. A trim adjustment. Nothing alarming. Yet, here's what we believe happened next, reconstructed by naval investigators over months of analysis using sound recordings, debris patterns, and engineering models. Somewhere in the engine room, one of those thousands of silver-brazed pipe joints, the very joints with that 14% failure rate, gave way. At test depth, that failure wouldn't have looked like a leak. It would have looked like an explosion. A jet of seawater forced through a small opening at over 1,000 pounds per square inch, instantly atomizing into a freezing, blinding fog. A fog so dense and so cold that within seconds it could short-circuit electrical panels throughout the compartment. And here's where the nightmare compounds. That electrical short circuit would have triggered an automatic safety system, a system designed to protect the nuclear reactor by shutting it down the moment something goes wrong. It's called a reactor scram. In any normal situation, on the surface, this is exactly the right safety response. But this submarine was not on the surface. It was over 1,000 feet underwater. And the reactor wasn't just providing electricity for the lights. It was providing the power for the pumps that drove the propeller, the only thing keeping this 3,500-ton vessel from sinking deeper. With the reactor down, the submarine lost propulsion. And without propulsion at this depth, there is only one direction to go. Down. The crew would have known immediately what was happening. Trained men, the best of the best. They would have attempted an emergency main ballast tank blow, forcing high-pressure air into the ballast tanks to force the submarine back toward the surface. It's the submarine equivalent of slamming on the emergency brake and the gas pedal at the same time, praying it's enough. On the surface, the support ship's radio operator heard a final transmission. Just fragments, a reference to exceeding test depth. Then, a sound the operator would never forget. A sound like compressed air rushing through a system at maximum pressure. The sound of a desperate final attempt to save 129 lives. It didn't work. Chapter 4. The final second. Here is the part of this story that most documentaries skip over, because it is almost too horrifying to fully comprehend. As the submarine continued its uncontrolled descent, it crossed a threshold, a point of no return. Engineers call it collapse depth. The depth at which the pressure differential between the inside and outside of the hull finally exceeds what the steel can structurally bear. Up until this exact moment, every second of the dive, the hull had been holding, bending perhaps, groaning under the strain, but holding. The men inside likely had no idea the literal structure around them was now seconds, maybe less, from catastrophic failure. And then, collapse depth is reached. What happens next does not happen in the way you're imagining. It does not happen slowly. It does not happen like a flood. Naval engineers and physicists have calculated that a hull implosion at this depth occurs in approximately 1 to 2 milliseconds. To put that in perspective, the fastest a human eye can blink is about 100 milliseconds. The implosion of this submarine's hull would have been complete in less than 1/50th of that time. Faster than a human nerve impulse can travel from your hand to your brain. Faster than the speed of conscious thought itself. The air inside every compartment, air at normal atmospheric pressure, was instantaneously compressed by the inrushing ocean to a fraction of its original volume. That compression generates heat. Extreme heat. Studies of similar implosions suggest internal temperatures could spike to several thousand degrees Fahrenheit for a fraction of a second, hot enough to instantly combust anything flammable inside the hull. In simple terms, for the 129 men aboard, there was no flooding, there was no drowning, there was no time for fear, for pain, for a single complete thought. One moment, they were inside a submarine. The next, they were not. The wreckage didn't sink as one piece. It scattered. Investigators would later locate the debris field spread across an area roughly the size of 6 football fields, at a depth of approximately 8,400 feet, so deep that sunlight has never once touched that seafloor in the history of the Earth. It would take months for the Navy to even locate the wreckage, and the discovery would trigger one of the most significant overhauls of submarine safety procedures in naval history. Chapter 5. The aftermath that changed everything. In the months that followed, the United States Navy launched what would become one of the most exhaustive engineering investigations in its history, and what they found was both reassuring and deeply unsettling. The submarine itself wasn't fundamentally flawed in its design. Its hull, its reactor, its weapon systems, all sound. The failure came down to something almost mundane: quality control on thousands of tiny pipe joints, performed under wartime production pressure, by a workforce stretched thin. This single tragedy, born from a handful of imperfect welds, directly led to the creation of a program the Navy still uses today, designed to certify that every single component of a submarine's hull, piping, and pressure systems meets rigorous standards before that vessel is ever allowed to dive again. Every submarine built since has undergone testing and certification protocols that trace their lineage directly back to this disaster. In a strange and tragic way, the deaths of those 129 men became the foundation for the safety of every submariner who has served since. Every dive completed safely, every crew that came home. All of it stands, in part, on lessons learned at 8,400 feet. But here's the question that haunts naval engineers to this day. If a vessel built with the absolute best technology, the brightest minds, and the tightest oversight of its era, could still be brought down by a handful of microscopic flaws in pipe joints smaller than your thumb, what does that tell us about every other machine we trust our lives to, every single day? Because the ocean floor isn't the only place where pressure, metal, and human lives collide in a battle that never stops. And in our next investigation, we're going somewhere even more extreme. A disaster that happened not at 8,400 feet, but at 13,000 feet, involving a vessel that was never even built for the depths it dared to explore. If this story gripped you the way it gripped us while researching it, hit subscribe to Iron Edge Factory right now, because what we're about to show you next goes even deeper.